Welcome everybody to this first seminar in the CS area summer program. So today's speaker is going to be Rebecca, let's see here, Rebecca Hartman. She is the lead for the user engagement group at the National Energy Research Scientific Computing Center. She started her career at the Oak Ridge National Laboratory in Tennessee, spent some time in Australia, and then joined the NERSC, the National Energy Research Scientific Computing Center, in 2015. And today, Rebecca is going to tell us, the good things that happen at NERSC, all the scientific problems that are solved in NERSC hardware, computers. And next week on Tuesday afternoon, Rebecca will also be giving a crash course on high performance computing class that I would encourage all of you to attend, because she will be, presenting various interesting things. So with that, Rebecca, please you take control. I'll stop.
All right. Thank you so much. Thanks for the introduction, Osni. So yes, my name is Rebecca Hartman-Baker.
Nice seeing you, Rebecca.
Yes, I lead the user engagement group at NERSC. I've been at NERSC since 2015, and I'm going to talk to you today about the kind of stuff that we do. So let's get started. Okay. So high performance computing, we should start by defining our terms here, right? High performance computing is the application of supercomputers to scientific computational problems that are either too large for standard computers or would take them too long. Okay, so we use these computers to solve hard science problems that can't really be solved in any other way. So for example, we might want to design cheap and efficient solar energy resources. So, we could do a bunch of stuff in a lab and work on it that way. Mix some chemicals together or whatever. Or we could simulate it on a supercomputer, and that's the easier and cheaper and more environmentally friendly way to do it. So that is basically the starting definition here. I see there's a chat. Oh yes, please, yes, feel free to ask questions. Feel free to talk and interrupt me if you have a question, or raise your hand, or however it works. And for the folks in 3101, you probably want to go up to the front where the microphone is and ask your question there, so that I can be sure to hear it. Okay, so I just said we use supercomputers to do these great things. Okay, well, what is a supercomputer? Well, a supercomputer is actually not so different from a high-end desktop computer. The only difference is a difference of scale. So it has about 11,000 nodes, and which each node is kind of equivalent to a high-end desktop computer. So 700,000 compute cores that can perform about 3 × 10⁻16 calculations per second. That's what Corey here can do compared to your super high-end desktop. It's just a matter of scale, more or less. Okay, so if we want to translate that into something that people can understand, Corey is equivalent to if we had 4 million Earths. Okay, and each Earth has 7 billion people on it, and they do 1 floating point operation per second. So you may ask, okay, what is a floating point operation? A floating point operation is any mathematical basic arithmetic operation that involves a decimal point. So if I say 1.1 plus 1.1 equals 2.2, I just did a floating point operation. So, and I did it in 1 second, let's say. So if everyone on Earth were doing that, and there were 4 million Earths, then we could do as many computations as Corey can do in a second. So you could see, like I said, it's really a matter of scale. These supercomputers are super powerful machines that just are able to crunch lots of numbers really fast. Okay, but there's also more to it than just crunching numbers. So if you think of each node of the supercomputer as equivalent to, a desktop machine, these nodes are all connected to each other with a high-speed, low-latency network. So this is how nodes can talk to each other and work together in order to solve problems that you couldn't do on your laptop, not to mention on a whole bunch of laptops. So your typical bandwidth here we're talking about. So a supercomputer typical bandwidth is 10 gigabytes per second. And at home, if you're super lucky, you might have 0.02, so 200ths of a gigabyte per second. So we're talking a 5,000 times difference. And the latency is also really short. So on your supercomputer, you might have a 1 microsecond latency. Your home computer, probably a 20,000 microsecond latency. So you can see that this is a really fast, really specialized network that performs really well. And sometimes people use cloud systems. Cloud systems, they generally have slower networks than this. This is really tuned and created for this special purpose, not for the general purposes that most other networks are for. Okay, but there's more. So we also have petabytes of fast storage available for the files and data that are used in these computations and that are generated by the computations. So Cori has a 30 petabyte file system. Yeah. And this picture here is actually a picture of the file system. Your laptop has a, oh boy, these decimals are too small now. So a 5/10,000ths of a petabyte storage system on it. And your iPhone is even smaller. I'm not going to try to measure how many zeros there are. But you can see Cori has a huge file system to it. And then we got to write, we want to write data to this storage, right? We got to have a good bandwidth on that. And turns out we do. So on Cori, you could write about 700 gigabytes per second. Whereas on my computer here, sitting here that I'm giving you this presentation on, it is about 0.01 gigabytes per second. Now, cloud systems, they have some I/O, but the thing is, their file systems, that's where they make a lot of their money, is actually you putting data onto the file system and then getting it off of it for you. They make a lot of money that way. So anyway, that is some differences. So now let's talk more about high performance computing. So with high performance computing, what we're really doing here is parallel computing. So what we do when we mean parallel computing is we have some big task that we do, and we divide it up into smaller tasks, and then have each of the processors on the machine do one of these smaller tasks. You may have heard of the term divide and conquer. That's effectively what we're doing. So for example, let's say we're modeling the climate, right? So we could divide up the atmosphere into these sort of zones, and we could let each processor calculate one or more of the zones. Now, what happens though is, let's say that you're trying to calculate what's on the very edge of one of these rectangles. Well, you might need information from the neighboring rectangle, and that happens fairly frequently. So we do some communications between each of these little pieces of the work to maintain consistency between those pieces, so we can know the results of our neighbors and send our results to our other neighbors. So if any of this sounds kind of interesting, even if you don't quite understand what I'm talking about, I would encourage you to sign up for my course next week that I'll be giving about parallel computing, how to write programs using MPI and OpenMP. And we'll talk about how we create these algorithms. We'll talk about that a bit. And we'll provide some motivation for that that includes discussions of food, because I love food, and also puzzles. So if you're curious about that, sign up for my course next week. Okay, moving along. So these types of systems that we have are called distributed memory systems. So you might also see it called a cluster system. So you have these nodes, and they have their own local memory and distinct memory space for a processor. And a node typically has could have multiple cores in the processor, could have multiple processors. So on Cori, each of our nodes, there's two different types of nodes. One type of node has 32 cores per node. Another type has 68 cores per node. And the nodes communicate over that network that we already talked about. And then typically the way that we write these programs, and again, if you sign up for my course, you'll learn all about this, is called, thank you. It's called single program multiple data. I got a lovely flower from my daughter. Single program multiple data. So what this means is we write a single program and we execute it on multiple different pieces of data. So we do the same thing to different data sets. And we use what's called MPI to communicate data between the tasks when we need to. And again, if you're curious about that, sign up for my course for next week. You'll learn all about it. Okay. So now let's change gears and talk about NERSC. So NERSC stands for the National Energy Research Scientific Computing Center. And what we are is we are a national supercomputing center funded by the U.S. Department of Energy Office of Science. We support the SC research mission, and we are part of Berkeley Lab. So we are a division within Berkeley Lab. If you're a researcher who has funding from the Office of Science, you can use NERSC. Others can also apply if their research is within the mission of the department or the Office of Science. We have 8,000 users, and we have more than 800 projects that run on NERSC every year. And our users are from all 50 states, and we have users internationally in other countries. Almost 2/3 of our users are from universities, and actually the single largest demographic of users is students, graduate students and undergraduates. We have hundreds of users who are logging onto our machines every day. NERSC is the production, HPC, and data facility for the DOE Office of Science. So the Office of Science, if you don't know much about them, they are the largest funder of physical science research in the country. And so there's these 6 main areas where they fund research. So bioenergy and environment, computing, materials, chemistry and geophysics, particle physics and astrophysics, nuclear physics, and fusion energy and plasma physics. So we have projects running on NERSC that are in all of these different areas. So our mission at NERSC is to accelerate scientific discovery at the DOE Office of Science through high performance computing and data analysis. We love science, we care about the science first. So our users produce some amazing, groundbreaking scientific results. So you can see these are some of the highlights from recently. Materials science, trying to figure out how to make better solar cells, the components within it that will collect the solar energy and transform it into electricity for us. Earth sciences, we've got some folks who are working on Antarctic ice. As we all know, there's big icebergs that are falling off of Antarctica, and it's scary what's happening there, what's going on there. Advanced computing area, so like we've got scalable machine learning going on. We want to learn how to make machine learning work on a big supercomputer like that. It's not completely obvious. It's not as simple as a lot of the other problems that we do on these machines. High energy physics, so shedding light on luminous blue variables. I actually don't know what that means, but it sounds very impressive. Nuclear physics. I happen to really like nuclear physics, although I'm no nuclear physicist. So, we want to understand the structure of the nucleus. Like, why are there some nuclei that are stable and others are not? Like, who knows? Well, nuclear physicists are trying to find that out, and they're using simulations at NERSC to do it. All right, plasma physics. We've got plasma propulsion systems for satellites. Wouldn't that be super cool? We could just do that, and we don't have to worry about how to propel systems, satellite systems. So at NERSC, we are mentioned in more than 2,500 publications every year from scientists. And actually, from what I know, we are responsible in that sense for more publications than any other HPC center in the world. So it feels pretty cool to be working at a place like that. Okay, we're also really proud of our Nobel Prize winners. So we've had these users at NERSC, and they won Nobel Prizes. Like, how cool is that? Very cool. So we've got some interesting prizes here, but our most recent one that we were affiliated with was the 2015 Nobel Prize. So this was the discovery that neutrinos have mass and oscillate between different types. That's something that wasn't clear until they did these experiments and computations. So you see this picture here. This is a picture of the giant instrument that they used to try to figure this out. But what our role is that they performed calculations at NERSC, and they stored their data also at NERSC. So I think that's pretty cool. That's about as close as I will ever get to an actual Nobel Prize, but it's cool that people like me were around to enable these other people to win a Nobel Prize. Okay, so I got a few science stories for y'all. I think are kind of cool, things that we're up to, or our users are up to, I should say. Okay, so the first thing is the unfortunate reason why I am here in my home office and you are there in the building at Berkeley Lab or in your own home office. COVID, right? So we want to get rid of it. We want to figure out how to treat it really, when people get it. So there is the LINAC coherent light source, and that is at the SLAC National Accelerator Laboratory. And they use that to kind of take X-ray crystallography of the structure of the SARS-CoV-2 virus that causes COVID-19. So they do this, right? They make like these pictures of it, and then they want to do some calculations and analyze that data so they could figure out what picture do we need to take next. So they did this. They made these pictures. They sent them on over here to NERSC, and they ran in real time, or as close to real time as they could, these evaluations of that data. And then they got a result back, which informed them of what their next run was going to be like, what their next picture was that they were going to take. So otherwise, you just kind of have to randomly guess like what your next picture should be and stuff. But this way, they were able to really figure out what the best pictures that they could make in order to get the best information out of the experiment. So I think that is a pretty cool application of high performance computing. Okay, so another one. So here in California, probably not all of you are from here. We have earthquakes. We have quite a few. We had one just last week that woke me up in the middle of the night. Anyway, we want to find out what's going to happen to buildings when there's an earthquake, right? We don't want to find out from experience, though. We want to find out by simulating them. And so that's what these folks, David McCallum and his team, that's what they did, is they did some simulations to figure out like what happens with a tall building. What, how does it shake when the earthquake shakes the earth? All right, so next one. So if you're from the Midwest, I am not, but I did spend 7 years in Illinois getting my PhD. And so big storms, you know, especially tornadoes and things, those are a pretty big deal that you experience a lot in that part of the country. So they want to kind of figure out about these storms and also why they seem to always target, you know, certain buildings, let's say. Well, so what they were able to figure out from this was that actually there are these aerosols, which is particles suspended in the atmosphere that are produced by humans or human activity. And those can make the wind gusts stronger. They can make it rain heavier and make even bigger hail and even steer storms towards cities. If you've ever noticed that, it does seem like they seem to, like the big tornadoes seem to come in and rip out like the edge of cities a lot of times. So anyway, they used our supercomputers to simulate these things and figure out why this is happening the way it is. All right, last but not least, another COVID one, because I know we all hate COVID. So we have these researchers at Berkeley Lab, and they do this thing called the Materials Project. And they wanted to apply the skills that they had learned from the Materials Project to COVID-19. So what they did was they did some text mining of all of the COVID papers and literature that is being put out. And they developed this knowledge portal, that's what they call it, called COVID Scholar. So you can go to that URL, covidscholar.org, and you can find out what they've found out. So they're looking through all these papers and trying to draw insights and get connections between the research that may not be readily apparent to you just from reading it, but that the text mining and machine learning and natural language processing can make these inferences for you. So anyway, that seems like a pretty darn cool application of supercomputing resources too. Okay, so in 2020, our scientists used 8 billion NERSC hours. So that's greater than 1 million single CPU years. And just for your erudition, Homo erectus was around about 1 million years ago. So if Homo erectus had gotten started on using a CPU, he would be done about now with everything that we did in 2020. Okay, and they store more than 220 million gigabytes of data at NERSC. I mean, that's the equivalent of 4 million iPhones. We have these really cool data storage systems. I think the coolest one is our HPSS system, and it actually is a tape drive. And it stores more than 200 petabytes of data dating back to 1976. If you look at this picture here, we've got the it actually uses like this little robotic arm, and like if you're like, I need my data, right? It'll use this little robotic arm. It'll go find the tape that your data is on. It'll grab it off the shelf. There you can see those tapes on the shelf there with the barcodes on them. It'll grab it out of there, and then it'll shove it into this tape drive, and it'll read off your data. And it'll retrieve your data within 6 seconds. That may sound like a long time, but compared to if someone had to manually go in there and find your data, it's a really short time. So that's pretty cool. But this is kind of the deep storage of data. Kind of like when you're cooking and you put something in the freezer, like frozen blueberries or something, which you don't get out very often. I'd say the HPSS system is kind of equivalent to your freezer. Okay, we also have another system called the Community File System, it stores 64 petabytes of data for users on that system. And users are able to access that data directly from all of our compute systems and other resources. So I think those data storage systems are pretty interesting. All right, now, like I said, we give out time on our supercomputers, and this is kind of a breakdown of how everything was divided up recently. So you can see we've got sort of different areas, and this is their usage, how much they used in terms of compute hours. And those numbers, like chemistry and geoscience, that's in millions. So that's 1.29 billion hours that they used on our supercomputers. So next I'm going to talk about some challenges in the high performance computing field that I'm hoping that you young people can help us resolve. So one of our biggest challenges is power usage. So we use a lot of power. I don't know if you all are aware of this. You know, like at home, your power bill is probably in kilowatt hours, right? Our power bill at NERSC is in megawatt years. Okay, so we use multiple megawatts of power per year. So the problem is with computing resources, yeah, they're getting more and more efficient, but we're kind of reaching an upper limit here. So if we just keep making them the way that we are making them, then eventually they'll melt because it's such high power, such heat in such a small area. So we're already, you know, up to like sun surface level heat on some of these processors. So that's not good. So a trend that we have seen is that compute cores are just going to get slower and simpler, and we'll have a lot more of them on a chip. So take GPUs, for example. They have a whole bunch of really lightweight cores on a GPU, and they're good at one thing, and that's doing arithmetic. So that is kind of the way that things are going. But there's a limit to that sort of thing, right? We can only get so many more on a chip. We're going to run out of space. So we really need some revolutions in energy efficiency. So our energy efficiency is increasing, but the thing is that the top supercomputers today use tens of megawatts of power, and you can figure you're spending about $1 million per megawatt per year. So typically you can get about 4 to 5 times the performance by doubling your power bill. But you know, doubling your power bill, that's a lot. That's not scalable, right? You're gonna, we're getting up to the point like, you know, the newest machine at Oak Ridge Frontier. I mean, it's, I guess it's about maybe like 40 megawatts or something like that. So you're spending $40 million a year on power alone, not to mention everything else that you need for a machine like that. So we need to develop more energy efficient technology for our facilities. So there's this measure called the PUE. I don't actually know what PUE stands for, but it's the measure of energy efficiency in the operation of a data center. So if we operated perfectly and we had no overhead whatsoever, our PUE would be 1. So at NERSC, over the past year, our PUE has been at about 1.08. So we have kind of an 8% overhead. So for every watt that goes into the supercomputer to run it, we have to use 8% overhead in order to cool it down and take care of the machine, basically. So you can see we are pretty energy efficient. It's only 8% overhead. considering that the data center industry average is a PUE of 1.67. So we are actively researching facility energy efficiency here at NERSC. So we've determined that data centers can actually operate outside of the human temperature comfort zone. So, if you go into a machine room and it's 100 degrees, you're going to 100 degrees Fahrenheit, I should say. That'd be like 38, 38 Celsius. So let's say 40, just to give ourselves round numbers. So 100 or 40, depending on which temperature scale you prefer. But if you go in there, it's going to be super hot. You're going to be very uncomfortable. You could get a heat stroke or something, right? But computers are actually fine at that temperature. So that's something that we've learned. We had one time we had a very hot day, and we thought we were going to have to turn off the machine, so we kind of paused it and slowed everything down. But then a later analysis revealed that we actually didn't need to have done that. So those machines can operate at very high temperatures. Another thing that we've done is we've automated some intelligent fan and water settings. So these machines, they are typically water cooled. So they have these pipes of water that run through and that cool down the air that is inside of the machine, basically. And they also use fans to kind of push that air through. Now, what we've figured out is that we don't always have to have the water at the highest setting going through. It kind of depends on what the temperature is within the machine and the ambient temperature of the room. So we don't always need to have it at the highest setting. We can turn it down, we can turn it up, depending. Also, the same thing for the fans. When we first got the machine, I think the fan had 3 settings, and it was like off, low, or high. But now we have, I think, more than 20 settings for the fan. So we can change the volume of air that is coming out of the machine depending on the external conditions. And we're also always looking for more ways to reduce our PUE even further. We'll probably never get down to 1, obviously, unless we invent a perpetual motion machine. We can't get 1, but surely we can go down from 1.08. Okay, so another thing is we kind of talked a little bit about programming, and I, shamelessly advertised my course for next week. But programming for advanced architectures, such as a CPU with a GPU for offloading, is very challenging, actually, both to program it in the first place, but also to get good performance out of it. So we have people working at NERSC who just want to do some science, right? But they end up having to become an expert on computer architecture and programming models. And that's not their expertise. That's not what they're interested in. So that's kind of unfortunate. It'd be nice if we could make it easier for them. Another thing is that the performance on one architecture doesn't always translate to performance on another architecture. So maybe I have my code running really well on Perlmutter, which is our new machine at NERSC, but I want to go run it on the machine at Oak Ridge. Well, we'd have to tune the performance to make sure that it would work well on their machine. So that's kind of unfortunate. And then also, we just have a lot of what you might call legacy codes that haven't been ported over and that are kind of unsuitable for this type of architecture. So we might have to just completely rewrite those codes. All right, another thing is there's something called Moore's Law. It's really more of an observation than a law. So back in the 1970s, Moore observed that computer chips doubled in performance every 18 to 24 months. So we were able to follow this trend for quite a long time because we were able to miniaturize and we were able to put multi-cores on a chip. But there's an end to Moore's law, and it's soon, if not already. So then the question is, what do we do next? How do we get better performance? So this is probably going to come in the form of brand new architectures that we don't really understand or know a lot about yet. So accelerators, maybe. I mean, that's what we're doing right now with GPUs. FPGAs, maybe. Quantum computing, maybe. For some applications, quantum would actually be a really good choice. But then let's say we think those are the way to go. How do we even program for those? Yeah, like, I don't know. I don't know how to write a quantum program. Probably almost no one does. So so these are questions that, you know, we need to start trying to answer. Okay, next challenge we have is data. So data is always getting bigger. So weird, right? We have simulations because we're able to do bigger simulations. Those bigger simulations are able to produce more data. We have scientific instruments that are getting more and more advanced that are producing more data. So I used to, as we mentioned, I used to work in Australia. And one of the things we were preparing for in Australia was the square kilometer array, which is a giant telescope with a imaging area of a square kilometer. So when the SKA comes fully online, it will produce more data in one day than currently exists. If you could just kind of think about that, that kind of blows your mind, but that's the case. It's going to just be so much data. How are we even going to store that data or examine that data or analyze it? Ooh, nobody knows. How are we going to be able to transfer that data from the very remote area where the square kilometer array is centered in remote Western Australia? How are we going to access the data? If the data is in Australia, you know, networks become a big deal. How do we get, you know, data from that place to this place where we want to analyze it? So we really need to figure out efficient workflows for data analysis and data management. So I wasn't just saying all those things as a laundry list of things that I need to do, because they're not. It's actually challenges for you all. So if these things are intriguing to you all, you know, there's great career options out there to try to study some of these elements and figure out what we can do. So you all consider whether you want to help us to figure out how to program the next generation of machines, figure out how to make sense of all of this new data that's coming in, how to build faster, more capable hardware that is more energy efficient, and how to design our facilities so that they are even more energy efficient. How do we create effective data and job management workflows? How do we bring in new fields of science into HPC? I mean, for example, the COVID thing, that's a relatively recent addition, not just because COVID didn't exist before, but you know, that type of research was not something that we saw a lot of in supercomputers. And then, of course, we want you to do all these things and tell the world about what you're doing. And that is my presentation. I left plenty of time, I hope, for any questions that people might have.
I have a question.
Yeah, sure.
Yeah, so how did you get into parallel computing or NERSC in general, if you could give more background stories about that?
Okay, so how did I get into this field? That's an excellent question. So I always loved computers and computer programming, but I actually majored in physics as an undergraduate. And I did a summer research experience similar to what you all are doing, where I simulated physics on a computer. And I just thought that would just completely married all of my interests. So it was so cool that you could simulate physics on a computer. So after that, I went to graduate school in computer science at the University of Illinois. And to make a long story short, I had to find a way to support myself because I wanted to do research that my advisor didn't have money for. So I found an assistantship at NCSA, which was a supercomputing center, similar to NERSC, at the University of Illinois. And so after that, then I saw how cool that was and to use supercomputers. So that's how I got into the field. I guess the rest is history.
Thank you.
Yeah, thanks for the question. That was a good question. PUE, yes, power usage effectiveness. Thank you. Okay, are there any other questions? Well, you all may have questions about how I was getting flowers. That was my daughter. She's 7. Today was her last day of school. And you may have heard some interesting sounds going on behind me. That's my son.
Oh, what?
There he is. He's 15.
Hi,
We are office mates.
for the last day.
This is the last day. This is the last day of school.
Any further questions for Rebecca?
I have a question.
Yeah.
Please.
So,
I'm
do
on
you-
90 man now. Yes.
Okay. Sorry.
yeah,
It's
no
just
worries.
fine.
How do you protect all of the data at NERSC from cyber attacks? And is there any backup data storage location for NERSC if there were anything bad to happen here?
That's an excellent question. So how do we protect NERSC overall? So NERSC is always a target. You know, if you're a hacker, wouldn't it be awesome if you could say, I hacked a US government Department of Energy facility? That would be super cool. Like you could get some huge cred on that. So so we have a lot of things in place to protect NERSC. Now, of course, I'm not an expert in this area, but I can sort of give you an overview of what we have going on there. So so the first thing is that we have constant monitoring and surveillance of our border going on. So we use this product that's called Zeek, Z-E-E-K. Used to be called Bro. And so Zeek, basically what it does is they collect all this information about all of the activity that's coming into NERSC. And they analyze it and they look for patterns of things that are, you know, potentially cyber attacks, sort of things like for example, you know, there was like that, what was it called? Was it called like WannaCry? I want to say, I don't remember, but there was some kind of vulnerability in Intel processors, and so we were able to reproduce the sort of activity that one would be looking for if that was happening, and use that as a pattern that Zeek is looking for when people are on the machines. So we do SSH key logging. So whenever you type stuff into your SSH connection to one of our computers, we're recording everything that you do. And another thing is that we are able to prevent or make it more difficult for someone to have a compromised account, because we use multi-factor authentication. So if so when I want to log into NERSC, I have to provide both a password and a one-time password. And actually there was a case of a lot of HPC centers in Europe got hacked last year or the year before. None of them used MFA, and so we believe that our MFA actually prevented those hackers from being able to come and hack our supercomputers. So as for your data, like how safe is your data? So it would be difficult, I would say, for people to access NERSC and get to your data, because we do have a very active and excellent, really, security team who's on the case all the time. I guess what we would probably notice if there were, because like I said, there's all this key logging, there's Zeek, there's everything. We would probably notice if something irregular was happening, and I think we'd be able to shut it down pretty quickly. Oh, I should mention too that we are always, there's always people trying to do a denial of service on us. And so we do block a lot of IP addresses that are exhibiting that type of behavior. We also block IP addresses from certain countries that the United States calls state sponsors of terrorism. So countries like Iran or North Korea or other countries like that, we just block anything coming from those countries. So I would say your data is probably pretty safe on NERSC, but if you want more details, I could definitely connect you to our security team who would be able to tell you a lot more.
Rebecca, there's
you.
another question there in the chat. I don't know if you see it.
Okay. Okay, I understand that. Oh, okay, for the course. C, C++, or Fortran is recommended for the course. I currently only know Python and Java. Okay. Okay, Kristen, that is a good question. So what's going to happen in the course is we're going to write code in C or Fortran. So Java and C++ are kind of, similar languages in a lot of the syntax. So I would say you might not have too much trouble there. A future project is definitely to try to do some of this in Python, but that is not going to happen by next week. But I do think that Python, has become a very popular language even in high performance computing. So I probably should try to accommodate that as well. So I hope that was a somewhat satisfactory answer. Okay, and how can you sign up for the course? You should look through your email. I know that Lisa Brzezinski has sent out a lot of emails to you, but there is one that has this course in. So if you kind of search for the words crash course, you should be able to find the course. And also, I should mention that my colleague Helen He is going to be giving a course this afternoon about how to use NERSC resources. So I highly recommend coming to that one as well if you want to learn more about how to use NERSC.
I actually had a question just regarding like the education track when it comes to perhaps working at NERSC or pursuing a career in supercomputing. What would you consider to be perhaps like the best major, perhaps minor, to go into something like quantum computing or to go into some of these advanced simulations that are done at NERSC?
Oh, wow. Okay, so that's a really good question. So I wouldn't say that there's a best major. I would say, though, there's a lot of different choices. So a lot of the people in my group, such as Helen, for example, I'm going to pick on Helen for a second, so I just mentioned her. Helen has actually a background in environmental science, like climate science. But when she did her PhD, her thesis, her dissertation was computational in nature. And so I would say any science field that you're really interested in, to sustain your interest, to sustain your ability to do it, any scientific field that you could do a thesis or work of a computational nature, that would work. So most of the people in my group have a degree in a science field rather than in computer science. So computer science is an option too, though, if you like computer science, that's good too. Also mathematics, like especially applied math. And then as for quantum, I can tell you, you can work in just about any field for that. So of course, if you work in, chemistry, they do a lot of quantum simulations, and physics similarly. But the folks in my in NERSC, we have two quantum experts in NERSC, and I think one is a computational chemist, but the other is an applied mathematician who is working on algorithms. So yeah, I think those fields are wide open to people from a variety of backgrounds with a variety of experiences. It just kind of depends on what you actually want to do within that field. So if you want to design algorithms, then applied math is a really good choice. If you want to run, like operate a supercomputer, like be a system administrator, then computer science could be a better choice. It just kind of depends on how you want to go.
Thank you.
Yeah.
Any further questions for Rebecca? If not, thank you very much, Rebecca.
Yeah, thank you all for listening, and I appreciate your questions, and I hope to see some of you next week.
All right. Bye now.
Bye.
Thank you.